good morning. It is Monday, January the 25th, a rainy Monday. Those of you at home are probably still in bed. I wish I was, but we are here reviewing thermochemistry. All right, so now, what I'm going to be going over is what's in your Princeton Review for 2021, but the 2020 actually has some extra questions, and I'm going to post those, and I'm going to recommend that you do those, and later on today I'll post the answers and solutions to all of those as well, just to give you more practice, a wider variety of problems, what you should expect for the test. And after we kind of go over what you guys just did, we'll talk about the test itself and what you really need to know. But really, we've kind of gone over almost all of it already. So, your number one is this number 7. Which says that 1.5 grams of sodium nitrate is dissolved into 25 milliliters of water, causing the temperature to increase by 2.2. So as soon as I see the temperature is increased, is it endo or exothermic? Exothermic, okay, so that's the first thing. It probably doesn't ask about that, but that's just something that you need to know. Temperature goes up, it's exothermic, which means delta H is going to have what sign? Negative. And if it's endo, which is kind of, again, counterintuitive, because you would think if temperature is going up, delta H would be positive, but again, we're looking at the surroundings are going up. The system, which we're measuring, is going down. But we can't really measure the system directly, so we measure the Q loss equals negative Q gain. We measure how much does the surroundings absorb, and we assume that's how much the system released. Okay? That's why it's kind of opposite of, as far as signs and what we think. How can you take heat out, but the temperature goes up? Because we're looking at the surroundings, not the system. We're measuring the system, but observing the surroundings. Are we all good with that? All right. That's a hard concept to get your brain around, so I work hard to try to get you on with that one. The density of the final solution is 1.02 grams per milliliter. Which of the following expressions will correctly calculate the heat gained by the water as the NaNO3 dissolves? So, Ben, what was your question?
I got D, but I didn't know why you didn't add in the 1.5, because I thought you had to do the water plus the solute.
You do, but I think the density of the final solution, because they don't tell you, the mass. You can assume that it's 25 grams, 25 milliliters, 25 grams, but they're just going to have you use this density
of the
final solution. Okay. Which I guess is 25 times 1.02.
Yeah, because the volume stays the same.
Does it say that assume the volume of the solution remains unchanged? Which, if really, does it come out, what does it come out to? What does 25 times 1.02 come out to? Now notice that this is a multiple choice, so you don't really have to do the math, you just have to know the setup. But what is 25 times 1.02? 25 point, or really only 25.5? Okay, which means that the 25 milliliters of water wasn't really 25 grams. It was really only 24 grams. All right, so it's just a different way of giving you the mass of the solution.
Okay.
All right, so we end up having, so it's really Q equals MC delta T when it's saying which of the following expressions correctly fit heat gained by the water. Well, heat gained is MC delta T. This first part is just the mass of the solution. The 25 milliliters times the density gives you the mass. So they just combine the density question in with a specific heat question. All right? We all good with that? And then your number 2, well, we wanted to do number 3, what was asked about, which is this one, correct?
Yeah.
A student studies 2 solutions. A has a volume of 100 milliliters at a temperature of 25. B is 1,000 milliliters, but it's at 22. Which of the following statements must be true regarding both solutions? Okay? Solution A has more heat than solution B. Okay, is that true? A is at 25 degrees, but it's 100 milliliters versus 1,000 milliliters at 22. Okay? That's kind of iffy, but you have 10 times more water. So when you talk about total heat, that 10 times more water probably has more total heat than the 100 milliliters. Because there's only a 3-degree difference. The specific heat capacity of A is greater than B. What determines the specific heat?
The amount of energy to raise a degree.
But does water change? Does the specific heat of water change? No, it's always going to be, if it's water, it's 4.18. Okay, now if it's ice or steam, it's different, but if it's water, we use 4.18 from 0 to 100 degrees. Okay? If the solutions were to be mixed, heat would transfer from B to A. Would heat go from B to A? No. Okay? And then solution B has more thermal energy than solution A. Okay? Solution B. See now that, to me, has more heat and more thermal energy is really the same thing. Okay? So I'm going to say, I haven't even looked to know the answer. I'm going to say that this is the correct answer because we just have that 1,000 milliliters. But so here's a terminology thing. Thermal energy, heat, synonymous. So this is just asking the opposite, giving the opposite statements. Okay? A has more heat than B, or B has more heat than A. I don't really like that question. It's not really a great question, and I wouldn't stress about it too much. Probably the best takeaway from this question is the fact that thermal energy and heat mean the same thing. Okay? Any others?
Can you do the one right below that too?
Okay?
11.
Is this visible still on the camera? Okay? Based on the information, what is that? So as soon as I see the terms average bond energy, what has to come into your mind?
It's the bond, the energy to break the bond.
And bonds broken minus
Bonds created.
bonds formed. That's how you're going to get delta H. Okay? So as soon as you see this has to be a trigger in your brain for the equation delta H equals bonds broken minus bonds formed. Okay? Now, and go ahead and come over here. So delta H, bonds broken, we're going to have to break 2 hydrogen to hydrogen bonds. Right? So we find that the hydrogen-hydrogen bond is this. So it's going to be 2 times 500 plus 1 oxygen to oxygen bond. So the oxygen to oxygen bond is 500. 1 times 500. Minus bonds formed. Now remember we have H2O. There's 2 oxygen to hydrogens in each one, and we have 2 of them, so how many OH bonds do we have? 4. Okay, that's where a lot of people miss the boat on this one, is counting the total number of bonds. You simply, a lot of times they just multiply by 2. So it's 4 times the OH bond of 500. Okay, so it's really 1,500 minus 2,000 gives you a negative 500. You are expected to do that without a calculator. Okay? Notice I make the math nice and easy, but you are going to have to be able to do that without your calculator. Anything else?
On multiple choice or free response?
Any.
Okay. Can you do both for your
Both free response? Yeah. Okay, now number 3, we went over at the very beginning of the unit with this graph. Keep going up here. This is your number 1. Okay? Is it not?
It is.
It is.
I am, right? I'm just making sure Okay, so without even doing any of this, what state are we in here?
Solid.
Solid. What's happening here?
Melty.
Melting. And then this is,
Liquid.
and then this is, boiling, and then this is gas, okay? So the horizontal is a phase change. Why is that at a constant temperature? Why doesn't the temperature change? That's a good question. You put hot water on the stove, once it gets to 100, it starts to boil, but it never gets above 100 degrees. How is that energy being absorbed by the water or by whatever substance you're heating? What happens to water when you boil it? It's breaking the bonds. Now, which bonds are breaking? Is it the covalent bond between the hydrogen and the oxygen? Or is it the hydrogen bonds between the water molecules?
Hydrogen.
The hydrogen bonds, right? Because it's still H2O when it's steam. But whenever you break bonds or form bonds, what type of energy is that? You got a 50-50 chance. It's either kinetic or potential. It's potential energy. When you break bonds and form bonds, it's potential energy. Okay? What does temperature measure? I've heard a mumble. Kinetic energy. Okay? Average kinetic energy. So if you're changing potential, if you're breaking bonds and forming bonds, you're changing potential energy, which we use the term latent heat. It's hidden to the thermometer. Okay? So when we're going here, that's why we can say, well, ice melts at 32 degrees Fahrenheit or 0 degrees Celsius. But water freezes at 32 degrees Fahrenheit or 0 degrees Celsius. The melting point and freezing point is the exact same temperature, but they don't have the same amount of heat. Water has more potential energy than the ice does at the same temperature. Because when you go from ice to water, you've broken that bond, so you put energy in because it now has the potential to release that energy when the bond comes back and water freezes and makes the ice. Okay? So it does work. You put energy in to break the bond. It's now absorbed that as potential energy because it can release that same amount of energy when it comes back together. Does that make sense? Okay? So phase changes involve changes in potential energy, which is why we use the heat of vaporization and the heat of fusion when we're calculating the amount of heat. It's not a temperature change. We don't use MCAT because there's no temperature change. We have to use the heat of fusion as a measure of the potential energy difference. Anytime we have a temperature change, it's a kinetic energy difference. Anytime we have a phase change, it's a potential energy difference. The internal energy is the combination of both, but that's the one that we can't really, it's impossible to measure. We just measure the differences. Now, a couple of things else. Why is this line so much longer? Why is the boiling line so much longer than the melting line? I don't know. Am I answering some of these questions down here? Okay. Why is this line greater than that line? Why? When you melt it, what do? Are you breaking the molecules completely apart? You're just stretching the bonds and allowing them to roll over one another, right? So you're not having to put as much energy in, but to boil it, you have to completely break the bonds apart and separate them completely. So it takes a whole lot more energy to completely break the bonds than it is just to stretch them and bend them and give them some motion. Okay? So boiling always, the heat of vaporization is always going to be greater than the heat of fusion.
So heat of fusion is going from solid to liquid?
Yes.
Okay.
Now that's the positive, solid to liquid.
Okay.
It's the exact same number if you're going liquid to solid, but just negative.
Okay.
Okay? So it's 334 joules per gram to melt it, and then 334 joules per gram is what would be released when it froze. Okay? So once you get water down to 0, you still have to extract more heat to make it become ice. Okay? Because those bonds are beginning to form, and that's releasing heat to the surroundings. We got to keep removing that heat that's being released as it's forming bonds. Okay? So negative 334 is released, or 334 joules is released to the surroundings. And again, remember, I think I talked about the peach farmers, that they spray the peaches down with the water when it's going to be a mild freeze, because as that water freezes, it releases that 334 joules to the surroundings, which is the peach, and then the ice can act like an insulator, so it keeps the peach from freezing solid and getting ruined. Now that's only gonna work for a mild frost, it will not work for a hard, deep frost, which is why peach trees don't grow in the north. And so, which is why I don't live in the north. All right, so that's just kind of the basics. So here, anytime we have a temperature change, it's MCAT. Anytime we have a phase change, it's mass times your heat of fusion or your mass times heat of vaporization. And I might even put those equations, MCAT here, M times heat of fusion here, MCAT here, M times heat of vaporization on boiling, and then MCAT on steam. Because that's how you calculate delta H for each part. And remember at the very beginning of the unit, we went through and calculated all the different Qs. There's like 5 Qs, depending upon where you're starting, to go the whole distance. Okay, you have to do each one independently. Lastly, last thing I want to say about this, because obviously I'm thinking that this is important. Why is this slope less than that one? So in other words, C. Is the specific heat of the solid the greatest? Why?
Because the heat is more, like it's covering more heat in the liquid phase.
So
Well, it's the slope is higher, so it's.
the specific heat's gonna be,
Increasing fast.
the
It's gonna be
temperature's
yeah,
increasing
the
faster
specific
with
heat's gonna be lower.
less amount of heat being added, right?
So lower.
So what does that mean about the specific heat?
It's gonna
It's lower. The price of a degree costs less energy than, so which one, where is the specific heat gonna be the greatest? This one really, this slope right here should be nearly the same as this one. This is the, one of them's 1.95, the other one's 2.02 for ice and steam. I don't know which one's which, but the water's 4. So this really is not a good graph because it needs to be a little bit steeper. This one is gonna be, you know, the specific heat's twice as great for the water. So the takeaway, the fatter, the lower the slope, the higher the specific heat, which means it takes more energy to raise a given amount of degrees. All right, so now let's go through this. Which is greater, the heat of fusion? We already answered that. The heat of fusion or the heat of vaporization, and why? Somebody say now what a good answer is. Which one's greater, first off? Fusion or vaporization? Vaporization. Why?
Because it takes more heat and energy to break apart the bonds completely than just stretch them.
There you go, perfect. Hopefully that was close enough to the camera that you heard it. Okay? If additional heat is added to the substance, the line would continue at its current slope and not become horizontal again. Why is this?
It's already in the gas.
It's already in the gaseous state, they're already separated, they're just, so as you increase the temperature, what's happening to the molecules?
You're getting farther apart.
Farther apart, but what else? Kinetic energy increases, which, how do we measure kinetic energy, or what does that mean? Energy of motion. The molecule's gonna be moving just faster and faster and faster. And there really is no upper limit to how hot you can go. Now, for water, at some temperature, the hot water would actually decompose. You'd put enough energy to break the hydrogen, the covalent bonds between the hydrogens and the oxygens, and they would break apart. But then the hydrogen and oxygen would just start moving faster and faster. That would be that's not considered part of this graph. And then reading the graph, the specific heat, we just talked about that one, the specific heat, and then what would be the signs of the enthalpy and entropy changes as heat continues to be added? So as we're adding heat, what's the sign of enthalpy? Positive. Does it take energy or release energy to melt ice? To melt ice.
Yeah.
Do you put it on the stove or you put it in on the freezer? To melt ice. Stove. You add heat to it. You're going positive. So everything in this way is a positive delta H. Everything coming this way is a negative delta H. Okay? Energy going in to cause those changes. So when the water vapor condenses and makes liquid, it's going to release energy, which is why steam will burn you way worse than boiling water, because it has the same kinetic energy as the boiling water, it just has all that extra potential energy that's going to get released to the surroundings when the steam water molecules come together to make liquid water. The energy you put in to break them apart is released when they come back together. All right, what about entropy? You're going from solid to liquid to gas.
It's gonna increase.
It's going to increase, okay? As you increase temperature, entropy increases. All right, does that make more sense now to you? That's important. You're going to need to know this information tomorrow. Just saying. I'm not even implying. I'm saying. All right, I see the word calorimeter in here. So I'm thinking Q loss equals negative Q gain right off the bat. Okay, I'm thinking, okay, I'm going to put something hot into something cold, or I'm going to be measuring how much heat is absorbed by the water. That's going to be my heat of the reaction. Okay, so, but this is, okay, so your initial temperature of aluminum. So this is your hot object. This is your water, cold object. So which way is heat going to flow?
System to surrounding.
Well, but is it going to go from the aluminum to the water, from the water to the cold go to the aluminum? Okay, remember, it's just that temperature determines the direction of heat flow. So the energy is going to flow from this until they reach, quote, thermal equilibrium, which simply is a fancy way of saying same temperature. Thermal equilibrium means same temperature. So, given that the specific heat of water is this, and assuming the density is exactly 1, calculate the heat gained by the water. Okay? Now, what we have here is you have, what is it, how much water? Student heats a piece of aluminum as it drops in 25 milliliters. So we assume the density is 1, so that means how many grams? 25 grams. And it's at 23.2 degrees. And then we're going to take a chunk of aluminum that has a mass of 5.86 grams, and it's at 109.1 degrees, and we're going to drop that into here. Now, is the aluminum going to dissolve in the water? Doesn't aluminum dissolve in water? No. So we don't have to include that in the mass like we would if it was dissolving. So we only have 25 grams of water. So to measure the heat of the water, the Q gained is going to equal MC delta T. So the mass of the water is 25 grams. Specific heat is 184 or 180? Times my delta T, okay? And then you have the final temperature here, so that you can just subtract, and remember it's always final minus initial. Temperature went up, so it's going to be positive. It's 3.6 degrees, right? So that gives me 2 sig figs. So technically your answer should only be 2 sig figs. And what does that come out to?
380 joules.
How much?
380 joules.
380 joules. Okay? So the 380 joules was absorbed by the water. Where'd that energy come from? This is the Q gained. Where did it come from?
The aluminum.
The aluminum, right? So the Q lost, in this case, is also mass of the aluminum times specific heat of the aluminum times the change in temperature of the aluminum. The Q lost equals Q gain. When we're putting a piece of hot metal into cold water, the metal's losing, but again, it's the same equation because it's a change in temperature. We're not changing phase at all. The aluminum's just coming down in temperature, and we can always measure that by MC delta T. So this Q lost is going to be what? Negative 380, right? It's equal to the mass of the aluminum, 5.86 grams. Specific heat of the aluminum is what we're looking for. Now the change in temperature of the aluminum, always remember, it's T final minus T initial. So you can just subtract, but it's going to be a negative sign, so it comes out to negative what?
82.3.
Negative 82.3. Okay? And that's degrees Celsius. So then you just solve for C of aluminum, specific heat of aluminum. And if they did it right, it should come out to 0.9. But what did you get it? How much? 0.780. And that's joules per gram degrees Celsius, because we have joules divided by grams divided by degrees Celsius. Okay, so this is just kind of taking you through, instead of doing a reaction in the calorimeter, just putting a piece of hot metal. I think we even did one of those at the very beginning of the unit like that. Okay? Calculate the enthalpy change for the cooling of aluminum in water. The enthalpy change. Well, what was we already did that. What's the enthalpy change? Oh, in kilojoules per mole. We have joules per how much? It's this many joules were released by how much? Okay, so this is, which one is this? This is B.
Per 5.86
This is
grams.
B, this is A. So if I go to C, what do I do?
You take
Negative 380 is the amount of energy, right? Lost. How much kilojoules is that?
0.30.
So it's going to be delta H is going to equal 0.380 kilojoules divided by how much aluminum lost that much heat? Divided by 5.86 grams. But I want kilojoules per mole, so then I have to use what?
the molar mass.
Molar mass. So it's going to be 26.98, or you could use 27.0. So what do we get here?
$1.73.
1.73, and it's going to be negative 73 kilojoules per mole. That's the enthalpy lost by the aluminum in kilojoules per mole. This is a very, very, very important calculation to know how to do. Just saying, yes ma'am.
So the .780 is going to be positive?
Yeah, because negative here and negative here.
Now-
Specific heat is always positive.
For C, does the sign matter? Because in here they have it positive.
I think it needs to be negative, because obviously it's losing energy, so it's releasing it, so it needs to be negative. Sometimes just in the wording, how much energy was released. If it says release, you don't have to put the sign. So they're just calculating the magnitude of it.
Okay.
Okay, and again, the negative sign simply means energy is being released, so I don't think the sign matters.
Okay.
Okay? So then the specific, calculate, and if we go and come all the way over here, what's percent error mean?
Actual minus,
So it's gotta be point, what did we get, 780, minus what?
the,
0.9.
0.9, the accepted value, divided by
0.9.
0.9 times 100. Okay? And then when this, you subtract this out, you're gonna get 0.120. So you still have 3 sig figs. So your percent error should be to 3 sig figs, and it comes out to
13.3.
13.3. Okay, you just have to know that equation. That is not a given equation. You need to know. And again, AP is absolute value, so it really doesn't matter which way you go with this. But you always need to know you divide by the actual, not yours. You don't care, we don't care what your answer is. We're measuring how far off you are. So you always divide by the right answer, not by your answer. Okay? And then lastly, suggest 2 potential sources of error that will lead the student's experimental value to be different. So are we under or are we over? Okay, that's why I kind of like the negative sign on there. You know, AP takes absolute value. I like the negative because that tells me that I'm under by that much. Okay? So which, in our calculation right here in B, what's the only thing we really measured? The temperature, right? More than likely, you can put a piece of aluminum on a balance and get that one right. What's the main source of error?
Losing
As I'm going to take this is heated up, and I'm going to take it and I'm going to drop it into the water.
Losing heat to the surroundings.
Losing some heat to the surroundings before you drop it in. Right? So a lot of times you take it out of a hot source and then you just quickly transfer it into the water. But as you're moving it, some heat's released to the surroundings. So what does that mean about the delta T? What does that mean about my final temperature? It's too low. How else? What else could be a source? Same principle.
The cup itself, is it like,
Perfectly insulated, or the container itself absorbed a little bit. The styrofoam cup or the beaker or whatever you're doing it in, it absorbed the energy instead of the water, which would cause delta T again to be too small and your value to be under. So anytime you're under, heat was lost to something other than the water. If you were over, the only thing I could think of if you were over, say it came out to 1.1 instead of 0.9, is that when you put it down in here, your thermometer stayed at the bottom and you didn't stir it fully. And so the bottom got hotter than the top. Okay? That's really the only thing that would cause something to be greater, because almost always heat's lost to the surroundings, so it makes you go under for the delta T to be too small. But for delta T to be too big, you just have a hot spot, you just didn't stir well. All right? And now notice how they said, make sure you can quantitatively tie to the student's results. In other words, you need to be mentioning about delta T. That delta T would be too small, which would then cause Q loss to be too, or the specific heat to be too small. Okay? All right. See, the reality is that it's this delta T that's going to be too small, not this one. This one's actually going to be larger, so you're going to divide by a bigger number here to make that one smaller. Okay? All right. So, those are the two that we did. So now you have those other ones that I gave to you. You got 8 minutes or so you can go through and, thank you. Try to work on those. You can work on them at home if you want to and study. Okay, the test is 25 multiple choice questions and 3 problems. Now the 3 problems have multiple parts, okay? But you need to know calorimeter problems like this. You need to be very familiar with the heating curve, okay? And in the different parts, you need to be able to know Big Mama, okay? Delta H of formations. You need to be able to know that you calculate delta S in 2 ways. You can either do it with products minus reactants, wherever the entropries of formation are given, or delta G equals delta H minus T delta S. In that equation, delta G equals delta H minus T delta S, what's the most important thing to make sure? Not the signs. That's important to pay attention to the signs. What's the unit on delta G and delta H?
Oh,
Kilojoules, right? What's the unit on entropy? Joules. We gotta make sure we match the units. Okay, when you use delta G equals delta H minus T delta S, make sure you match the units.
On the, when you do products minus reactants, is that the one that you don't count the pure elements, like they're gonna be zero?
Delta H is gonna be 0 for elements. Okay?
But
Entropy, they have a value.
Okay, alright,
But delta H and delta G, they do not.
okay.
Okay? And then for the elements, that's almost, those will be given in a table. So sometimes remember there's two variations for using Big Mama. Well, that Big Mama equation is really the same for entropy and free energy. It's products minus reactants. Okay? Remember you always multiply by the coefficient. That's your moles. And it's, you either find delta H given all of the heats of formation, or you have delta H and you have all but one of your heats of formation and you have to find that one. We did problems like both of those. You can do that for entropy as well, okay? One other thing I would suggest possibly as a study tool, in that Princeton review, in the pages before the multiple choice, they give a little synopsis about all the different things that we talked about. Oh, by the way, you have to know Hess's law as well. That just made me remember that as we're obviously visualizing those different sections. But I would go through and just read the written part, the theory part on that Princeton review, because it's your whole chapter in your textbook, 5 and 19, all condensed into 3 or 4 pages. Just getting the highlights, getting the important stuff. That'll be a good review, that's all you need to know. Okay? Does anybody have any other questions?
How do you know when you need to like divide by the coefficient to find moles, or like use the mole mass to find moles? It's like sometimes we do a kilojoule for like if it's 2 moles, we divide by 2, and now we did a mole mass. How do you
Okay. That's a really good question. You're gonna, when the delta H is given to you in an equation, okay? It's either gonna be given to you in terms of 5.86 grams reacted and gave off this much heat, or they give you the delta H in kilojoules per mole. If they give it to you in kilojoules per mole, so we're just gonna say 2H2 gas plus O2 gas goes to 2H2O liquid. And then it's gonna tell me that my heat of formation of water is equal to negative 285.83 kilojoules per mole. Okay? Now, if I wanna know, do anything, this is per mole, so this is 2 moles being made. So the amount of energy released from this reaction is going to be times 2 moles. But if I said 5 grams of hydrogen, how much energy is released when 5 grams of hydrogen? Then I'm going to change this to moles, say how many moles I have. But I'm still going to have to multiply this by the negative 285 kilojoules per mole. Because then that's going to tell me how many moles actually reacted. Okay? Now, if it gave me the delta H here of 2 times that, which would be 571.6, okay, kilojoules, just kilojoules for this reaction, then I would have to divide by the 2. Because this is not kilojoules per mole, it's just kilojoules per the reaction. Or sometimes they even say per mole reaction. So in other words, as the reaction's written. Okay? So this is how here, so we would, to get per mole, we'd have to divide by the 2. That is the confusing part of this. Hopefully I explained it.
Could you just give like a brief, definition of Hess's law?
That the equations add together, the delta H is added together.
Okay, like the lab.
Yeah,
Okay.
just like the lab. Okay? And generally, a clue that it's a Hess's law problem is going to be that you have multiple equations given.
Okay.
You have to have at least 2. To do Hess's law, you have to have at least 2 equations. And so that's where the one that we did as a practice problem, they had the one where it was a solid going and making the gas, and then it was I2 solid going to I2 gas as the second equation, and then we just had to set them up to where they canceled out. Okay? I'm just saying, you need to know how to do that. Okay?